Thank you for coming to my talk here at the European Conference on JavaScript. We're slowly achieving domination. It is taking time, but so far, so good. I am talking about concrete types for TypeScript. TypeScript is an extension to JavaScript that adds types, but they're unsound. Let's make that a little bit more strong. So, here's this thing. It's called StrongScript. It's mostly compatible with TypeScript, with a few caveats. We've tested it on lots of code. Okay, you know, we've tested it on the compiler and the things that come with the compiler and that sort of thing and a few benchmarks, but it's still plenty of code. And we can say that when you add types, you get a little bit of speed up, at least in some benchmarks which we all know to be meaningless. But that's still a number. And those types can be sound when you want them to be. Okay, that's StrongScript, thank you. Okay, I guess I should maybe say a little bit more about it. So, some of our goals here. What were we actually trying to make with StrongScript? So, in some sense, this is a replication study. There is an earlier system called Thorn. Thorn has a few similar ideas. Thorn wasn't JavaScript. Thorn wasn't compatible with or even trying to be compatible with JavaScript. We would like to sort of bring that in. We would like to demonstrate that when you add types, you can get speedups, right? I mean, practical programmers know that. And being in the terrible, terrible universe of JavaScript, we would like to deal with at least some of the real-world problems and real-world constraints that JavaScript implies. And of course, we live on top of TypeScript. So, being this TypeScript-based, TypeScript-compatible language, our actual system looks like this. You have StrongScript code, you compile that into JavaScript code, you can run that on any JavaScript engine. But we have an extra little arrow here, which is that you can actually get some speedups if you have a specialized engine. Ours is based on V8. Okay, so that's the idea. That's what we want to build. And why? Where do we live? So, you're going to see a very similar couple slides to, an earlier presentation this morning in terms of what the landscape of these languages, where you can sometimes put in type annotations and sometimes not, is. On one side of this gulf is languages like typed racket, soundness, huzzah. On the other side is languages like Strongtalk, but of course, both of these are far more busy than any of that. And this gulf is soundness, by some definition of the word. And in the lower left here, you'll find most of the languages that industry is very happy with and or created. And in the upper right, you'll find most of the languages that have papers published and might actually have some guarantees of something. Guarantees are nice, industry usability is nice, and so we're trying to sort of bridge that gap. Not to say that we're pseudo-sound or Schrodinger's sound, but that soundness is something you can choose. We want to give soundness to the user. If you need it, you can have it. If you don't, you don't have to use it. You're not enclosed by it. So what does that mean? Well, here's a very simple example. So this is a class, maybe an ECMAScript 6 style class or TypeScript style class. It's something called a point. We can imagine that a point can be added to another point, and it would also have this method called add3 if you want to add 3 points together. And to add 3, well, we're going to start by adding 2 of them and then add the third. So this add3 is going to call the regular add function. And then down at the bottom, because we are brilliant JavaScript programmers, we're just calling it with some strings. I'm sure strings are enough like points. And what will happen here? Well, because JavaScript doesn't have types, we're kind of living in a world like duck typing, and what will happen is this isn't a method. In fact, we'll get trying to call undefined as a method, but any JavaScript programmer will understand that as this isn't a method. So that's certainly not ideal. And thus, gradual typing has one answer to that. And what'll happen? Well, we'll still get an error at the same point in runtime, but it's the right error. The error is wrong argument, and specifically, it's a wrong argument not here in the middle of this random add3 code that doesn't seem to have any problem at all, because in this environment we can say, point came from here, and that doesn't match that, so now that I reached this point, I can tell you the wrong argument was actually add3. So that's good. We get the right error, we get it a little bit late. But it's not free. And the reason that we can get the right error, and the reason we can draw those arrows, is that we need to wrap things to know sort of where they belong, what their location is. So we're making a wrapper that says, this is the wrapper of the string high as a point. Okay, honestly, we probably could detect very quickly that the string high isn't a point, but generalize this to objects. The string high as a point, and some information on where in the code this happened. Same for the string ho. And then those wrappers are what flow into the actual function call, and those wrappers are what get asked. And when the method isn't found, then the wrappers can say, aha, it is because of this location that that method wasn't found. That is, of course, if it actually makes it that far. Because if the bad bit of the wrapper is never invoked, nobody cares. It works just, it works in the sense that it runs. Okay. So we're looking for a compromise. We're looking for something where we can get the error where we want it, we can get something like duck typing when we want it, and that we don't have to pay this price. We don't have to have wrappers everywhere that are going to be expensive. So here's strong script. So far, it looks exactly the same. And if I run this code, I'll get method not found exactly like I was in a duck type setting, or indeed TypeScript. So I haven't gained much, but what I said was I'm going to give soundness as an option to the programmer. The programmer hasn't asked for it, and so the programmer got exactly what they would have gotten with TypeScript. Now let's ask for it. Okay, how do you ask for it? Well, you say bang point, meaning concrete point. And what this means is I want to be really, really absolutely sure that point never refers to anything that isn't a point. And punct never refers to anything that isn't a point. And of course, in order to verify this, in order to guarantee this, you pay a bit of a price. This has to actually be a point. It has to have been built with new point. You are restricted to that world. But we get the error where we expected it to, and that line, point.addPunct, doesn't fail. And so now we have this option. We have the options we had with TypeScript, which are at the far left, and I don't mean that as a political statement. The far left, we have the any type, where anything can just be any type in the world, and that's exactly what you have in JavaScript. Somewhere in the middle, we have the TypeScript types, being both those that sort of fit well into the static world of Java and such, classes and primitives and that kind of thing, and a few things that don't fit quite so well into that world, like function types, interfaces, which is TypeScript ease for structural types. And then if you're willing to go to the far right, again, not a political statement, for some set of those types, we can give you soundness. But this is a spectrum. I'm not saying that you have to choose one. The whole point is you don't have to choose one. You can mix and match. You can mix and match as much as you want. You can have a structural type that has members that are primitives, that are concrete primitives. You can have members that are functions that return concrete primitives. You can have concrete class types assigned to structural types if they structurally match and get more or less the errors you expect. In this case, well, P is of type iPoint. So if I say p.x equals hello as a string, that's a static error. I statically know that a string cannot possibly be a number, so we can check that ahead of time, no problem. P.y, that's going to be a runtime check. Why? Well, I didn't know anything about iPoint. This is living in the TypeScript world, so I don't have that soundness. But the whole point of bang number is I'm supposed to have the soundness, So we check it as soon as you go between these two worlds, as soon as you go from the unsound TypeScript world to the sound StrongScript world. I'm sometimes very loud, by the way. And similarly, if you call magnitude, well, magnitude itself we can't check, but we can check its return. Its return is a bang number, so when we call that, we get a check. As soon as you move from the TypeScript world into the world of strong types, you get a check and you get a guarantee. And so what can you do with this? Given that system of types, what can you build? Well, let's start with this very ugly sort of completely untyped thing. We have some function. This function is going to check if p.x is less than 10 and return 10 in that case. Otherwise, it's going to return p.dist. And then we're going to call it with this object. And this object is just something we built out of the blue that has an x and a y. It kind of looks like a point. That thing kind of looks like it's supposed to take a point. And so this should be fine, right? And it is. It evaluates to 10. That's an accident because we don't have p.dist, but we never called p.dist either. But this does still evaluate to 10. It accidentally works. Well, accidentally works isn't very good, so let's try and strengthen this a little bit. And let's try and strengthen it in basically the TypeScript way at first. We're going to define this type in a more complete way. Rather than implicitly by how it's used, we're going to define this type as an actual class and say a class point is something that has an x, which is a number, and a y, which is a number, and this magnitude thing, as we showed before. And now the f function, we expect a point. This blob, we say that is a point. That's what we think this blob is. That's what it's supposed to be behaving as. And again, this works, except because we have these types now, these TypeScript-like types, at least we get some local guarantees. We don't have soundness. We don't have the guarantee that a point is always a point, but at least we have the guarantee that if I said it's a point and then I say p.dist, there is no dist on point. I can use magnitude instead. So I get all the local guarantees of TypeScript, but nothing much more. Okay, we want to harden it a little bit more. Now we want concrete types. So we throw bangs all over the place, everywhere where that makes any sense. Bang number, bang point. But this is a get what you pay for language. So now, that isn't a point anymore. This thing isn't a point. We're going to get an error. We have to buy into the system of using new point because we said bang point, but we get the guarantee that this new point actually has a magnitude. We don't randomly miss something that was supposed to be there because statically and dynamically, we know that as soon as you get into f, that really truly is a point. On the other side, so that was sort of the obvious and direct things. If I say I have a new point and then I try to use it wrongly, well, in this case, I said that's an any reference. So p.x equals beer, that can't statically fail. You can do anything with an any reference. This is any typed, just like in TypeScript. So statically, that's got to be fine. But we did say that it has to be a bang number. So again, a check happens. And this happens at runtime. So there's the checks when you're explicitly calling in, but there's also the checks when something is explicitly protecting itself. Now, if we actually said this was a point, even if we say it's a point and not a bang point, now we have the type, now we get static type checking. We get exactly what we expect. Okay, so that's the universe we live in. Let's summarize again. TypeScript, all the joys that TypeScript gives us, and then for some subset of TypeScript types, you can say bang that for classes, for primitives, and now we're going to get checks and an actual guarantee that that really truly is the thing that we said it is when we get there. So what does that give us? Now that we have this system, this world to live in, what do we actually gain from that? Well, soundness, and we have our own particular definition of soundness. No two people agree on what soundness means, but maybe we can get 1.5. What I mean when I say soundness is if I have this line, obviously bang C means some object that is of type bang C, that method invocation cannot fail. I can't get a type error from calling a dot method on bang C. But it's a get-what-you-pay-for method system. To get that, I had to pay by actually verifying that I have a bang C. I have to know, it has to be statically known. This has to be an actual truth. In terms of dynamic interoperability, well, again, it's a bit get-what-you-pay-for. If you can fit into the TypeScript-y world, if you don't need concrete types and concrete checks and the actual soundness guarantees, then instead what you can get is interoperability with dynamic languages, or with dynamic JavaScript code, that is. And so what we can say is, if you have a program or a program segment that has only any types, and you add non-concrete types to it, those are erased, like in TypeScript, they don't affect the execution. You're not going to break anything. So you can get dynamic interoperability when you need it. You can get soundness when you need it. What about the universe in between? Well, in terms of code evolution, if you can get to the point where you have something with entirely non-concrete types, but you want more sort of structure to it, and you're not using any, you're not using downcast or other nasty things, you can move. You can add bangs everywhere where bangs can go, and the code will perform exactly the same. So there's a story here. You can move from JavaScript to some types. That's good, step in the right direction. You can move from some types to concrete types. Or if there are little bits where you care about the concreteness but you don't care everywhere, they can all interoperate with each other and do mainly what you expect. But of course, if you do interoperate between them, there is a performance cost, because if you have bang C, you're saying, I want to check that. I want to guarantee it really is a bang C. That's the syntax for a cast in TypeScript, if you don't know. And that does indeed cost. And the cost is a little bit hard to measure, but I seem to recall someone mentioning a system for measuring this kind of cost this morning, so maybe there's something to be said about that. I don't have what to say about it yet. But on the other hand, if we really truly know that's a bang C, and we get a member out of it, for example, well, that's like member access in Java. We know the exact type. We know exactly where this thing should be within that type. And in fact, we can compile that with some special intrinsics and get faster code. So you can take a performance hit when you're moving between them, but you can actually get a performance boom when you are in the concrete world.
Question?
Yes.
This is JavaScript, and the fact that you're trying to get a performance speed up in the engine means that when you say soundness, you need genuine soundness.
Yes.
However, JavaScript is everywhere mutable unless you freeze things.
Right.
So just because C used to have member doesn't mean it still has member.
Right. So we are living in the sort of ECMAScript 6 classes world, and so we can conditionally say more about when things are.
The classes expanded.
No. Yes, they're all, so in ECMAScript classes exactly as written, they're all still mutable. In order to get these guarantees, it's, again, get what you pay for. You're buying into a system where now you have protections on members. So that's part of the generation. But when you say bang C, you're buying those protections on members. That's, yeah. And when I get to the code in just a second, we'll see where that comes from. So in terms of how this generates, I said that this generates JavaScript code, and it does. That's not readable. Let's not try to read everything, but just to show sort of what's happening, when you try to translate the class model into JavaScript, there's a lot of boilerplate for that. That's a lot of it. There are some type checks, because indeed we had types there, and concrete types incur checks. As was just pointed out, there is some protection. So if you say that a member has to be a bang number, for example, we actually are going to generate accessors so that if somebody from the outside tries to get in, they are incurring the checks as well, and we're protecting our own members. Same goes for methods, because somebody from the outside, somebody from the JavaScript world, can call into our methods. We need to guarantee our own types there. But as expensive as all of that sounds, we can access things directly, rawly, when we are living in this world where everything is typed. So the class protects itself, it protects its members, it protects its methods, but we bypass that if we are in the typed world to avoid the extra overhead involved. That is just the plain JavaScript version of this, but I did say that we can also compile this to a specialized JavaScript engine, add some extra intrinsics. Well, the first one there is basically if you're accessing members on Bang C, we controlled how Bang C is built, or we controlled how classes are built. So that's like a Java access. There's no reason for that to be as expensive as a JavaScript access. So we can generate an intrinsic for that. For floating point numbers, we can generate intrinsics to skip all of the, is this a float, is it an int, do I need to do this kind of math, that kind of math, is it actually a string and not a float at all? Basically skip all of those checks, mostly things that would be checks in the JavaScript world. We can generate intrinsics to check. Those are handled by V8. If you want all of the details on that, see Adam Domerad's poster yesterday. So time travel required, oh well, or of course, look at the details in the poster or talk to us. So to bring it all home, concreteness can be a get-what-you-pay-for system, and strengthening and soundness can be a get-what-you-pay-for system. You can provide a system that actually gives you access to all of the options, and you get what you pay for. And of course, if you do get what you pay for, we can actually aid the VM and get performance boost rather than performance lost. So I said thank you for talking on this slide, or thank you for listening on this slide. I'll say thank you for listening again. I'm happy to take any questions.
Right, thank you. We have questions?
So if you have functions, one way to get soundness is with contracts, which wrap the function.
Right.
And but they have the unfortunate thing that when you wrap it, you've changed the object identity.
Right.
So sometimes if you add soundness by adding wrappers on functions, you can actually break it because the identities are different.
Right.
What happens in your system?
Right. So first off, we need to have a distinction between functions and methods, unfortunately, because functions of the arrow TypeScript function type live in this middle world where you can't have checks on them. You can't have a concrete function type. You can have a function type return a concrete type, in which case you check at the end when that function type returns, but not a concrete function type, so we can't check what that is. Methods are a different story because they are sort of part of a class, and basically you can call them as methods and get exactly what you expect, but if you try and strip them away from that class, then you lose that sort of special status, and they lose that the guarantees. They become any typed if you try to strip them away from the class entirely, or from an instance rather.
Okay, so one of the things you're telling me is that you cannot provide strong soundness guarantees for functions. Again, it's functions versus methods. For anonymous functions, the guarantees we provide are TypeScript plus you can have checks on the arguments and returns. So we're going to get checks at the right point, but not know where the blame came from, not know who's to blame. Right, I think that's what I said. You don't get strong guarantees.
Yes.
Okay,
Yes.
fair enough.
Yes, and again, it's because this is a get what you pay for system. If you want that, then you're going to have to buy into methods rather than functions.
So one neat thing about this work is it's looking at how nominal types play into the whole gradual typing story. And I'm still trying to come to grips with that. A lot of the prior work is with structural. The one thing I'm wondering about is, suppose you have part of your program is using point version 1 that has methods that have any types on all the parameters, right?
Right.
And then there's another part of your program that's using point version 2 that has all kinds of, the specific, concrete types or what have you on those methods. can these points interoperate with each other, or
So-
well, I think the answer is no. But correct me if I'm wrong.
Can the points, as in like instances of those points, or do you mean
Can I
code
pass-
compiled against one point?
Can I pass an instance of point version 2 into something that's expecting point version, well,
I
version
see.
1
Well,
passed into a version 2?
So if
framework?
you're talking about these both existing in a running system, then
No.
If you're talking about like code compiled expecting point version 1, code compiled expecting point version 2, that we can interoperate so long as the changes are in this direction of just adding more concreteness, any to C to bang C, not like any
But-
to C in
but
one
won't
case
the-
into something
but
incompatible in a different.
Won't the cast to bang v2 look at the object that's of type v1 and say, no, that's not the same type?
So again, we're talking in the system where you're talking about things compiled against different versions. You're not going to have.
No.
Right. So I'm saying if you have actual instances in the system of both, then
Right.
no, they can't interoperate.
Okay.
If we're talking about the
That was
system where
my-
you have something compiled against different versions, but you only are running with sort of one, then that.
No, it was
there's an
the first case
interoperability
that I was
story
asking
there.
about.
Yeah. The first case, those are different objects. They're different types rather. So
Right.
there's just
okay.
no.
So that's a distinct difference then between the structural versus the
Yes,
nominal
yes.
in this setting. Okay, thanks.
Any more questions? Okay.
So throughout this talk, you've been emphasizing choice a lot, that you have choice of how sound you want your system to be. But of course, choice can also be paralyzing, like you go to the grocery store and you don't know what peanut butter to get. So as a programmer, how do I know where I want to put these bangs in my code? Like for example, I might think I'll just put bang everywhere and then relax it until I'm happy. How should I go about putting these in?
So when I'm going to a grocery store, I just buy the cheapest peanut butter, and thus I would probably, in many cases, not put the bangs at all and be quite happy. But basically, the bangs are when there's something that you want out of it, right? And that might be performance. That might be that you're in some kernel where, no, this has to be this type. I don't think that it would be a ubiquitous thing in a real system until you've sort of moved it entirely to using bangs. I think it's more that there would be situations where if you don't care, if it wasn't something you wanted, then you didn't want it. If you do care, then you can buy into it. So I don't know if that completely answers, but it's something that you can basically ignore when you don't care, and thus you buy into it only when you do.
All right, then. One more question. Okay.
Would it be easy to configure your dev environment to add bands only in dev mode, so you get good error messages, but then to strip them in production, so you get basically speed improvements in production, but in your dev mode you have good error messages?
So I think if you wanted really good error messages, then you would want full gradual typing with wrappers and that sort of thing. And in a prototype, we did show that that can work in the structural setting, the TypeScript setting. But it basically, we didn't invent anything new, and so there was nothing to present about that. I think that if you cared about the debuggability, that would be where you were aiming, because if you move from C to bang C where you had no type errors, then you're sort of restricting yourself, expanding yourself. I mean, if it already worked, why? Because it already worked, and bang C isn't such an onerous cost. It can improve your performance and doesn't always reduce it hideously.
All right, then let's thank Gregor again.